Okay, so this is our demo for our code and schematics for our project for 2031. Our project is the math peripheral that helps us do multiplication, division, and modulo. So we start in the normal scomp BDF, and you can see our peripheral down here in the bottom left. As you can see, it just takes in the normal parameters, the reset flag, the address bus, the read and the write, because we need both of them, and then as well as the IO data as an in-out. And then if we go one step further into our schematic here, so we decided to go with a kind of a hybrid approach. So inside of here, we have our four different registers, our inputs and our outputs, and we decided to split it up into four registers if you've seen our register map. And so these four registers are operand 1, operand 2, our function type, and the result register. So all three of these first ones act very similarly because all they're doing is being written to by scomp assembly and then holding that value to be used by the final result register. So if we take a look at just one of them, so they're pretty much identical except for what they're storing and what they check for their address. So you can see this is the one for operand 1. And so again, it takes in reset, the address, and then the write, the operand 1 as an out, and then the IO data as an in. So basically, we define the signal called chip select, and it is 1 when the address is correct for this register, which is in this case I believe is 91 or 93, somewhere around there, and that the IO wants to write to something. Otherwise it's 0. And then we start a process, and if the reset is 0, then we just automatically just put 0 in operand 1 and reset it. But if we detect a rising edge of this chip select signal that we defined before, then we just simply latch operand 1 as IO data. And then that's it. So that'll be that. And then this is pretty much identical except for operand 2 and result. Or sorry, operand 2 and function type, it's going to latch IO data into their specific registers. And it's going to detect their addresses and their, it's a different address. But then the last thing is our result register. So this one's a little more complicated because it needs a few different things that are different from the other registers. So it still needs the reset, the IO address, but now we need the read instead of the write. And the IO data is still there, but this time it sends an out, not an in. And then we need both the operand 1, 2, and function type from the other three registers, which are connected as shown. You can see that their inputs come from here and plug in there. So the way that the device works as a whole is it takes in, you first ask the user to write to all three of those first registers. So you need to write what your operand 1 is going to be, you need to write what your operand 2 is going to be, and then you need to write what function type you want to do. So for example, in that third register of function type, if you want to do multiplication, you write 0 to it. If you want to do division, you write 1 to it, and if you want to do modulo, you write 2 to it. And then obviously you write whatever you want your operand 1 and 2 to be. Then once that happens, we define a few internal signals that's similar to the first one, just the chip select, as well as another result bus. So basically this is just what we're outputting to IO data at the end. So similar to the other registers, we just define chip select that when the address is correct for this register, and this time if it's reading from it, then it's 1, else it's 0. Then we start another process, and we define a variable called temp result because we need to change temp result pretty frequently in this process block. That's why it's a variable. And it's 32 bits instead of 16 because the multiplication doubles the bus size, which we'll get to later. So again, if reset 0, you just reset to 0. And then, but if we detect a rising edge, then we set a case statement that has to do with the function type. So it allows us to split up the code into very modular sections. So for example, this is multiplication, this is division, this is all division, and then this is modulo down here. So simply for multiplication, all we're doing is just setting temp result equal to operand 1 times operand 2, and then we're converting the type from a variable to just a standard logic vector of 16 bits, so we truncate it. This is signed, so it works with multiplication of negative and positive integers. For our division, which is again is just the 1 We first check if the operand 2 is 0. If it is, then we just say result is 0. That's the way we handle division by 0. But otherwise, we just simply, again, just do a result of the 2 divided and then convert to a standard logic vector. And that's the end of that one. And then if it's modulo finally, then again, we check if it's 0 as operand 2 just to make sure we don't divide by 0 on accident. And then we set temp result equal to the sign of operand 1 minus the operand 1 divided by operand 2 times operand 2. And basically, if you do a little bit of algebra, you can tell that this is just the standard modulo written as normal arithmetic functions. And then we, again, just set the result equal to that 16 bits. And then if for some reason the function type is written as some other non-defined function type, we just define a error code as just quad E so that you can pretty simply see if your function type is not recognized by the peripheral. If you wanted to add more functions, it'd be really simple. You just need to basically just add another, for example, if we want to do like sine, and sine was the next one we want to do, you just simply do this, and then you'd be able to get to another function by doing that. And that's pretty much it. And then except for at the end, when SCOMP decides it wants to read from its register, we just simply latch IO data as whatever is in result when chip select is 1. However, if it's not, then we just do not drive it, and we just have it as high impedance.
This will display a successful implementation of correct answers for the hangman. To begin, start with all switches in the down position. Then, pick any switch and flip it up and down in 3 sets. The first 2 sets will generate operand 1 and 2 in the middle display, and then the third set will generate the operator in the furthest right display. In this instance, the operator was generated to be 0, so we will be doing 9 times 0, which results in an answer of 0. To enter in an answer, flip up the switches that correspond to the binary of that answer. Then flip up the leftmost switch to submit your answer, and if it is correct, once you flip down, the next round will begin. Flipping the switch up and down in 3 sets will generate 3 more random numbers for the next round. In this instance, operand 1 is 11 due to the B display, which is in hexadecimal. 9 is operand 2, and then the operator is multiplication because in the furthest right display, it is 0. 11 times 9 is equal to 99, so we will be entering in on the switches of the D10 99 in binary. After these are entered in, flip up on the leftmost switch to submit an answer, and if it is correct, the score will increment by 1, which in this case, it will go to 2. Since that is correct, you flip that switch down, and then once every other switch is flipped down, the next round will begin. With all the switches down, the next round will begin. The unique aspect of this round is that the random number generation for the operator generated 2 in the rightmost display. This signifies that the modulo function will be performed by a peripheral, so the operation will be 2 modulo 7. When 2 is entered incorrectly, the score will increment up 1 to 3, and the next round will soon begin. In this next round, D is and F are operand 1 and operand 2, which represent 13 and 15 in regular decimal form. And on the rightmost display, 1 can be seen, which signifies division in our peripheral. So 13 divided by 15 is equal to 0 when using floor division. So once this is entered in, the score will increment to 4, and the round will be over. Now, the failing mechanism of the game will be presented. In this scenario, after random number generation, the equation 6 divided by 2, which should be equal to 3, is generated. 0 is entered in on all the DE10 switches, and then the leftmost switch is incremented 3 times. Each up and down motion represents 1 submission of an answer. There are 3 given attempts, and after all 3 attempts are used, the random numbers generated are reset to 0, and the next round is ready to begin. The previous example represented what would happen at the start of a round if incorrect answers were entered in. This next equation, 11 modulo 7, which should be equal to 4, represents what would happen mid-game as the score has already been incremented by 2. Again, in this situation, 0 instead of the correct answer is entered in along the DE10 switches. The leftmost switch is once again used to enter in answers, and following the third incorrect submission, the two operands in the operator will be reset to 0, but the score will not be reset and another round may begin.